guys. So we have developed a deep learning project called Dental-Vision. So oral diseases are surprisingly common, yet most people don't even realize they have one until it becomes serious. That really made us think, what if we could catch them earlier? So getting a proper medical diagnosis isn't always easy. In many areas, access to dentists is limited, and appointments can take weeks or even months. Even skilled professionals can miss supple sign and complex dental images. That's where technology can play a big role, helping support and enhance what dentists already do. AI, especially deep learning, has shown huge potential in medical image analysis. It can detect patterns that the human eye might miss, and it can even do better. So the idea behind this project is, can we use AI to assist in diagnosing dental images early, accurately, and at a scale? If we get it right, it could make a real difference. Yeah, next slide.
Okay, so I'll be speaking about what data set we have used and what data set we have used for this project. So initially, we used the oral disease data set from Kaggle. So it had like around six different classes of oral disease, like what is mentioned in the table. Like there was the disease called hypodontia, gingivitis, caries, mouth ulcer, calculus, and tooth discoloration. Initially, our data set did not have like the healthy images. It just had the other six categories. So with those images, we kind of trained our few of our deep learning models that we have built, and then we figured like the uh, deep learning model did not perform well on classifying the healthy tooth images. So we again went and searched for some healthy tooth data set, and we found one more in Kaggle itself, the healthy tooth data set. So from that healthy tooth data set, we got around like 260 images. But as you can see, the other different classes have around like 1,200 or 2,500 images on the other classes. With just 2,600, sorry, 260 images, like we data augmented it to get around like 2,600 images, so that there won't be any class imbalance for the healthy data set. So finally, our data set consists of like these seven different classes, including the healthy images. And as you can notice here, like the calculus and the hypodontia has some 1,000 images less than the other classes. So we'll get back to that. So I just want to point this out here. So yeah. So with the dataset being confirmed, like we kind of trained five different deep learning models, which includes like vision transformer, computational neural networks with, sorry, convolutional neural networks with attention, the one with efficient and a vanilla CNN, and we even tried to build a vision transformer from scratch. So let's see the architecture and how the image is being used for the classes. So initially, for the deep learning models to work better, we need to convert our images to a tensor, right? So in our data set, like each and every image is of a different dimensions. So we wanted to create similar dimension, similar sized images. So first we resized the every single image into a 224 cross 224 image. We'll get back to like why we specifically chose this size. And then we scaled each pixel of our image from 0 to 225 to 0 to 1. Just nothing but the each pixel has an R, red, green, and blue values, right? Those values ranges between like 0 to 225. So we kind of just scaled it to 0, between 0 and 1. And then we converted those images into a sensor of size 3 cross 224 cross 224. And then again, we normalized each channel, the red, blue, and the green channels from 0 to 1, which we already converted it from 0 to 225 to -1 to 1. This is because like in the hidden layers, the ReLU and the leaky ReLU works better. Actually, the what is it called? The gradient descent algorithm works better if we have a zero-centric uh, values. That's why we converted our channel from 0 to 1 to -1 to 1. This is our pre-trained VAT architecture. So initially, as we have mentioned in the previous slide, like we have converted an input image into a tensor of size 3 cross 224 plus 224. And then we are using a patch embedding, which consists of like 16 cross 16 patches. So like initially I spoke about like we resized every single images to 224 plus 224, right? So that is because like so in the pre-trained transformer architecture, we used a transformer model called VAT Tiny Patch 16 to 24. In that architecture, it accepts the input tensor to be of the size 224 cross 224. That is why we have resized the image to that particular size. So after the patch encoding has been done, we introduce a new token called the classification token and the position embeddings for that image. So the classification token is what being used by the deep learning model to learn to classify the input images. And then the classification head consists of like 12 transformer encoder architectures are stacked one on the other. And then finally, it learns to detect the output class, which is the one of the 7 different classes which I have mentioned in the dataset while explaining about the dataset itself. And these are the training and validation accuracy curves and the training and validation loss curves for our pre-trained vision transformers. So we trained our model for like 3 epochs. Since it was a pre-trained model with just 3 epochs, we were able to achieve like 92% accuracy, as you can see here. We have 92% accuracy. And the training and validation losses as well reducing drastically across the 3 epochs. And this is the classification report of our pre-trained vision transformer model. As you can see, the F1 score of calculus is far low compared to the other classes. This is because, like initially I mentioned, like calculus had some class imbalance comparing to the other classes, which is why the F1 score of the calculus is less compared to the others. Yeah. Yeah. So the CNN architecture, CNN plus attention architecture will be covered by Madhav. Up to you, Madhav.
Yep. So in CNN plus attention architecture, uh, the input images go through several convolutional layer. Uh, Here, model learns basic patterns like edges, colors, textures that are common in dental images. Not every part of the image is equally important. The attention layer helps the model zoom in on the area that are actually relevant to the diagnosis, like a cavity or a mouth ulcer. Once the important layers are identified, the model increases their weight. So it pays more attention to where really it matters and less to things like background or unrelated regions. The image features are then flattened and passed through a fully connected layer. This is where the model takes its final decision. This looks like caries, or this is a healthy image, healthy teeth image. Since the model is distracted by noise, it becomes more accurate and reliable. With attention, we can even visualize where the model was looking uh, when it made its decision, making it more trustworthy. Uh, Next slide, please. So Here in accuracy curve, uh, we can see that the accuracy increases consistently for both train and validation sets, which is a good sign actually. So from second epoch, the validation accuracy slightly surpasses training accuracy, which shows the model is not overfitting, which is good. By the fourth epoch, both the curves nearly converges at like 89% accuracy. So the model is stable and it learns efficiently. While going to the loss curve, both curve decreases steadily. So validation drops faster, meaning the model is quickly learning relevant features. And there's no sudden increase in validation. There's no sudden increase in the validation loss, which says it is not overfitting. Next slide. So this is the classification report. As you can see, the F1 score of calculus is like low compared to others. This is because there's no adequate images, like compared to all the other images. The images in calculus is comparatively low. Next slide. So coming to the efficient net architecture, um, just a minute. The model begins by taking in the image and passing it through an initial convolutional layer called the stem. So this layer shrinks the image slightly and starts picking up basic patterns like edges and textures. The MB convolutional blocks are the real workers of the model. So EfficientNet has 7 of these models. So each designed to process the image deeper and smarter. They are lightweight but powerful, using special techniques like depth-based convolutional and attention to focus on what really matters in the edge. As the image flows through these blocks, the model starts to recognize more complex things, uh, more complex things like going from simple shape to meaningful features like gums, teeth, edges, or discoloration. So it's like the model is slowly learning to see better, like moving in every step. After all the learning, the model compresses everything it understood using global average pooling. So instead of flattening everything like the older models which we spoke, it smartly summarizes the features, keeping things efficient and clean. Finally, it hits off everything to a fully connected layer. That makes the prediction whether it makes classifying the gingivitis, calculus, or healthy images. This is where the model makes its final call. Next slide, please. Yeah. So in the train versus validation accuracy, after 5 epochs, the model accuracy on the training improves from 69% to 90%, which is good. The validation accuracy also improves, but starts to flatten around like third epoch, which means the model is learning well, but may soon reach a performance plateau on which, yeah, the data is unseen. Next slide. So in the classification report, we see the same problem as we saw before. In calculus, the F1 score is actually low. We know the reason why, because there's no adequate images. Next slide. So we have attained maximum accuracy for the pre-trained VAT, which is like 92%. While going next, we attain like 88% accuracy for CNN plus attention. And then we attain like 84% for EfficientNet, and then 70% for vanilla CNN. And we also used our custom VAT model. So what we did is uh,
Data augmentation.
we did data augmentation by 10 folds. So
Yeah.
from 15,000 images, we just data augmented into 150,000 images. We converted, and then we could get like 10% accuracy. And then the overall accuracy percent, which is like 19%, is what we could achieve. This is not very good, so we are not going to talk about this model now. Next image.
So yeah,
Yeah.
so now I'll talk about the limitations of the current model. So we went with the pre-trained VIT model. But so some of the limitations of this particular model were that it had poor performance on phone captured images. That was mainly because of lighting, shadows, etc., due to the phone camera. And also in the training data, there was limited angle diversity. So most of the images were taken head on, and there were very few images taken from the sides or intraoral. And also, the current model assumes every image is a dental image. So even if you take images of cars or your chair, for example, it will still give you a report, and it doesn't have any means to recognize it's not a dental image. So one of the ways we can address these limitations is through data augmentation. Also, we can add more diverse healthy class images, for example, intraoral images or healthy images from the sides as well, and which would really help to improve the real world performance of our current model. And also, we have a small demo for you. So if you want, you can go ahead and you can scan the QR code and you can test out. None of these images are saved so that you can put your images as well. So I'll just go with the demo. So this is our particular website. So once you open it up, so you have an option to use your camera to take a photo, or you can take a high quality photo using the rare camera with zoom by someone else, and you can upload that image here. So first, I will go with an image which actually has visible carries. So you can see that it's correctly able to predict the particular class, and also it is able to give the next step as well. So for the next image, we'll go with another carries image as well, and we can see that it correctly is able to predict carries. And also we have one healthy tooth image. So this is a healthy tooth image. So we can see that it correctly predicts that it's healthy as well. And all of these images were downloaded, and it is not from the training data or the test data. And one of the limitations I was talking about previously, that it cannot recognize whether it's a tooth image or not, that you can see that put I upload an image of two dogs which are yellow in color. So yellowness is characteristics of gingivitis. So it does predict the dogs as gingivitis. So yeah, so that's all for the demo. And now we'll just go back to the slides. Yeah. So we have our final couple of slides here. So for the future scope of a project, so what we can do is right now our model is able to detect just a single class, either caries, gingivitis, or healthy teeth. So in the future, we can have multi-label classification. So suppose someone has caries and gingivitis. So it can predict both the classes, and it can use bounding boxes to show those specific diseases. And also we need to enhance the healthy class representation with internal images, that is inside the mouth images, side images of healthy class as well. And also we need to add robustness to edge cases. So people wearing braces, images with lipsticks, and it should be able to recognize non-dental images as non-dental images and point it out to the user to upload dental images. And also we can use GANs for data augmentation. So because the one of the issues with the vision transformer was lack of data, so we can use GANs to create a lot of data for data augmentation and make the model better, and also deployment and feedback loop. So once a user clicks their photo of the teeth, an actual human will classify that, like a dental professional will classify that image, and that is used to train the model again, which would totally improve the model accuracy. And yeah, I think that's about it. Thank you so much. So this is the QR code again for people who missed it. And also we are adding the link to the project report, the slides, and the GitHub in the link below. So yeah, thank you so much. So Maddie, Vicky, it was nice working with you. So you have anything to
Yeah,
say about this project? I mean, it was really
Yeah,
interesting.
thank you.
thank you.
Bye, guys. Have a great day. Bye.
Yeah, yeah. Bye bye.
Bye.